Welcome back. We continue our study of chapter 3 and we move to section 3.2 about the uniform boundedness principle or the Banach-Steinhaus theorem, which is a consequence of the bare category theorem. Okay, but recall first, what do we mean by the norm of a bounded linear operator between two normed spaces? The norm of the operator is the supremum of Tx, where x varies in the closed unit ball of E. Okay. And here's the statement of the theorem of this section. We have two Banach spaces, E and F. Actually, we don't need to assume that F is Banach, but we have to assume that E is complete, because we'll use the bare category theorem, which requires completeness. Okay. So we have two Banach spaces E and F, and we have a collection, an arbitrary collection of linear bounded operators from E to F. Okay. Could be countable, but not necessary. Okay. And we assume that Tix is bounded for all I. Okay. And of course, the bound depends on x. So for each x, Ti of x in norm is less than a certain constant that depends on x. Okay, so I can write it in a more specific way in this. For every x in E, there exists a certain constant that depends on x but does not depend on I, such that the norm of Tix is less than this constant. Okay, so this is, I would refer this to as condition 1. So this is my assumption. Then what is the conclusion? Then the norm of Ti is bounded, okay, which in terms of quantifiers means that there exists a constant independent on x and I, such that the norm of Ti is less than m for every I. Okay. Actually, there's no x here. Okay. But this is, of course, equivalent to what? This is equivalent to saying that the norm of Tix is less than m times the norm of x by definition of the operator norm. Okay. So note the difference between the assumption and the conclusion. Usually, of course, the conclusion implies the assumption, but the theorem states something non-trivial. State that if this is true, then this is true. Okay, and we had to put several assumptions that we have linear bounded maps, we have Banach spaces. If you just consider an arbitrary collection of maps between two matrix spaces or even Banach spaces, the conclusion need not hold. So try to give a counterexample, actually. Okay. So, yeah. So this is, as we said, can write the conclusion as there exists a constant m for every x for every I. The norm of Tix is less than m times the norm of x. Okay. So this bound is more precise than this bound. Okay. Because here it's mx can be anything. Here the mx is just m times the norm of x. Okay. So the order of the quantifier is very important. Okay, so let us go to the proof. Consider for each n, for each non-negative integer or positive integer n, consider the set capital Xn of all elements small x in the space, in the source space E, such that the norm of Ti of x is less or equal than n for every I. Okay. Then we claim that Xn is a closed set of E. Why? This is just a consequence of the continuity of Ti and the continuity of the norm. Because if you put Gi of x to be the norm of Tix, then Gi is continuous as a map from E to R. Okay, because it's a composition, the norm is continuous and Ti is continuous. Okay. And I can write Xn as the intersection. So Xn is actually the set of all x such that Gi of x is less or equal than n. Or if you like, x belongs to the inverse image under GI of the closed interval 0. Okay, should be familiar with this from the course in topology. Whenever we have continuous maps and large inequalities, the set is closed. Okay. And I can write actually Xn as the intersection over all I of these inverse images. So Xn is an intersection of closed sets, each one being closed because it's the inverse image of a closed interval. So this proves that Xn is closed. And on the other hand, the assumption of pointwise boundedness, let us say. So if you like, we can call the assumption condition 1 pointwise boundedness, and the conclusion uniform boundedness, okay, because M does not depend on X. So the assumption implies that E can be written as the union of all these Xn. How do I prove that? I take, it's very easy actually, it's just, so take an element X in E, okay? Then the assumption tells me that Ti of X is less or equal than M sub X, okay? So if we choose an integer n bigger than M sub X, then the norm of Tix will be less or equal than n. So X will be in this Xn. Okay. So now we can apply the Baire category theorem, but we need the completeness of E. So the Baire category theorem tells me that at least one of these closed sets has a non-empty interior. Okay? So accordingly, choose a point X node in the interior of this Xn. Therefore, by definition of an open set, there exists a ball, closed ball of center X0, contains in the interior, and therefore contained in Xn. So what does this mean? It means that for every X in this ball, X belongs to Xm. But what does it mean that small x is in capital Xm? It means precisely that Ti of X is less or equal than small m for every I in capital I. Okay, now how can I write an element X in this closed ball? As you know, I can write this ball as X0 times R times this closed unit ball, right? Because, or if you like, any element in this ball can be written as X0 plus RZ, where Z is in the closed unit ball. So I just replace X by here. Okay? We did this in the exercise of chapter 0. Okay? So this is equivalent to this condition. Ti of X0 plus RZ, norm is less than M for every I, for every Z in the closed unit ball. Okay, and now I use linearity of Ti, so this can be written as Tix0 plus RTiz. And if I use the second form of the triangle inequality, of course I can put the R because it's positive outside the norm. So the triangle inequality tells me that this term is less than this term. And so it's less than M. And therefore, if I add the norm of Tix0, I get this. So I should, yeah. So I get RTiz is less than norm of this plus M for every Z in the closed unit ball. Therefore, taking the maximum over Z in the closed unit ball, I get the norm of Ti. Okay. And that's it. So if you divide by R, we get that the norm of Ti is less than a constant. Okay. The constant does not depend on X. Okay. So this is the constant capital M. So capital M is M plus this norm over small r. Okay, so this concludes the proof of the Banach-Steinhaus theorem. Okay, so note that, as we said, we didn't use the completeness of F, but we used the completeness of the source space. Okay, now I will state two corollaries of this, two very important corollaries, three actually. The first one, so we have, once again, two Banach spaces and the sequence now. So the collection is countable now. So we have a sequence of linear bound operators from E to F that converges pointwise to some limit. What can I say about the limit operator? Okay, so first of all, the sequence of norms of Tn is bounded. Okay, so in otherwise stated, norm of Tn is less than a constant m for every n. the limit operator is linear and bounded. And the third, I can do an estimation. I can estimate the norm of the limit operator. The norm of the limit operator is less than the lim_inf of the norm of the sequence. Now, why did I use lim_inf? Because the sequence of norms need not be conversion. Of course, if it's conversion, then this is just the limit. But I will give an exercise where Tn is convergent pointwise, but the sequence of norms is not convergent. Okay, this is why I used the lim_inf. And by the way, nothing proves that Tn converges uniformly, just converges pointwise. Okay. So this is just a consequence of the previous theorem. So first one is just easy because this is just a restatement. Okay, so this is just capital M. Okay. Because if Tn of x is convergent for every x, then in particular Tn of x is bounded for every x. Okay, convergent sequence in the metric space is bounded. Okay. So point one is just the direct consequence. Okay, now as you may know, it's very easy to prove that the limit operator is necessarily linear because each Tn is linear. Okay, so just write the equation Tn of x plus y equal Tnx plus Tny, and let n tend to infinity, you get at the limit T of x plus y equal Tx plus Ty, and same thing if you multiply by a constant. So it's very easy to check that the limit operator is linear. But it's not quite clear that yt is bounded. So we start by using condition A. So there exists a constant m such that the norm of Tn is less than m for every n, and this precisely means that the norm of Tnx is less than this constant. Okay, I called it c, you can call it m, times the norm of x for every n and for every x. Okay, this is the conclusion of the previous theorem. Okay, so but as you know, Tn of x converges to Tx, and the norm is continuous. So the norm of Tnx converges to the norm of Tx, and since limits conserve inequalities, large inequalities, we get at the limit the norm of Tx is less than the constant times norm of x, and this precisely means that T is bounded. Okay, and finally we have to do this estimate. So we write the fundamental inequality relating the operator norm with the norm of the image. So the norm of Tnx is less than the norm of Tn, this is the operator norm, times the norm of x, or every x for every n. And now I let n tend to infinity. This guy converges to the norm of Tx. Now, as we said, this term here need not be convergent, and we'll give a counterexample in the exercises. But any bounded sequence has a lim_inf and lim_sup. So I should take the lim_sup on both sides. So lim_sup of this, lim_inf of this is less than lim_inf of this. But since this is convergent, the lim_inf is just the limit. And the lim_inf of this guy, I can put the norm of x outside. So just norm of x times the lim_inf of Tn. Okay? And this implies that the norm of T is less than the lim_inf of the norm of Tn. Okay. Okay, now I will just state two corollaries and you will prove them in the exercises. Okay? So the first corollary, if you have a Banach space and a subset B of this Banach space, suppose that for every element f in the dual of E, the set f of B, which is a subset of the real line, so the set of f of x, where x is in B, suppose that the set is bounded. What can you say about B? Yes, then B is bounded as well. Of course, the converse is true, so we have equivalence, if you like, because if B is bounded and f is, and so any element f in E star is continuous. So yeah, since it's linear, a linear continuous map transforms bounded sets into bounded sets. So if B is bounded, then this set is bounded as well. Okay, so this is just a consequence of continuity and linearity of f. But it's not trivial. The converse is not trivial. If f of B is bounded for every f in the dual, then necessarily B is bounded. Okay. So I suggest to test your understanding, take a paper and a pen and try to prove this, to deduce this from the Banach-Steinhaus theorem. Okay. And if you don't succeed, I will solve it in the exercise. But try at least to test your understanding. And we have a dual result, if you like. So if now we have a set in the dual of a norm space or a Banach space, then if the set of f of x, so if for every x, the set of f of x as f varies in this set B star is bounded in R, then B star is bounded in E star. So it's kind of dual statement. Okay. I write the set as B star x. Okay. Of course, the converse is true. It's just easy. Okay. So try to prove on your own these two corollaries from the Banach-Steinhaus theorem. Yeah, so this concludes section 3.2 and this video. So in the next section, I'm going to cover the open mapping theorem and some of its consequences. So thank you for your attention and see you next time.